All right. So we run hypothesis tests, we draw conclusions, but there's also always a possibility that we could make a mistake. So what kind of mistakes could we possibly make? Let's just think about this example that we just worked here, that the null hypothesis was that the true proportion of financial records that start with a 1 is 30% against the alternate, that it's not 30%, and we got a p-value of 0.005, and we rejected the null. So maybe come back to that perhaps. So recall the probability of a type 2 error is beta, and the probability of a type 2 error is beta, and the power is 1 minus beta. Oh, we've already talked about this, I'm sorry. So this is just kind of review. So the probability of a type 2 error, remember type 1 error, I always remember for type 1, the null is true and you make a mistake. Type 2 error, you remember the null is false and you make a mistake. So a type 2 error is a probability that you fail to reject the whole whenever the null is false. That's beta. Power is a probability you correctly reject the null when you were supposed to. So power is a probability that you reject the null when the null is false, and that's going to be 1 minus beta. These are going to be complements because they're conditioned off of the same statement, okay? So power is an important concept in stats, kind of. Basically, whenever you run a test, you want to show that the null is false, and you want to conclude that this is true. Well, if the null is false, the question then is, how likely are you to actually properly reject the null like you're supposed to? And that's exactly going to be the power of your test. So a powerful test means we have a high probability of rejecting the null when the null is false. So if we consider making a type 2 error, or if we want to explore the probability of rejecting a false null hypothesis, we need to remember that the null hypothesis is false. The true percentage is not 30.1%. So the first question you should ask yourself then is, well, then what is the true percentage? The main factor that influences the power of the test and the probability of making a type 2 error is the difference between the hypothesized parameter and the true parameter. So in this case here, it's not going to be your sample. Your sample is just another number also, but we got a sample of 0.227, right? So maybe the true value is, I don't know, 0.24 perhaps. So the question then is, what is the true value? The difference between the true value and the alternate, the hypothesized value is called your effect size. So in this case, our effect size would be the absolute value of your true parameter, 0.24, minus the hypothesized value, which was about 30%. So that's about a 6% effect size. It's simply the difference between your null and the true, okay? For some reason, kids have a hard time with effect size. I know it gets a little abstract perhaps, but so in class we kind of explored this applet to look at how effect size changes the power of the test. I'd like to do that in this video as well. Here, let me pause it while I fire that up. All right, so this is an applet that will calculate power for us. So we can set our hypothesized value to 0.301. And normally we'd select a two-sided. I'm going to just select a one-sided just for illustration purposes here to kind of keep it simple. And I just realized that this is this is a applet for means. Yeah, whatever. I guess it'll still illustrate it, I guess. Sorry. Then this is going to be our alternate hypothesis. It says means, but it doesn't really matter, I guess. I do have a proportion applet, but yeah, I'm sorry about this. All right, let's just do this, I guess. All right, so we can still talk about it, even though this isn't really the right applet. We can still talk about power. Basically, let's just pretend we're talking about proportions and forget that these say means over here. So this is the this is the sampling distribution you're basing your decision off of. This is the hypothesized distribution. If you look at the center of this, it's centered at 0.103. What you are assuming is true, and then we make we'll reject the null if we get a value that's small enough. Basically, if this area here, if we run our test at a level of 0.05, a significance level of 0.05, this area here is going to be 0.05. So there's going to be some value here, some p-hat value, some critical p-hat value that if our sample proportion is less than this value, then we're going to reject. This distribution down here is the distribution we're actually sampling from. This one is based off of the true proportion of 0.24. So 24 is right here. That's where this one is centered. Since this is the true value, this is where we're actually getting our sample from. So the question then is, okay, if we're going to reject if our p-hat is less than this value, then what's the probability that in this distribution that we're actually sampling from, we get a p-hat that is less than that? And it's just the area to the left of that critical p-hat cutoff. Again, it sounds confusing, but it's really not too bad. But I do want to show you right now our power is 0.69. If I increase the effect size, so if I make the true value smaller, let's say 22%, notice this is 0.30, this is 0.22 now. As you increase the effect size, it makes the difference between those two curves greater, and it increases our power. So what if it's 0.1? This is going to be really, really high, like 100%. If the true value is 10% and your hypothesis is that it's 30%, then you're going to reject the null almost every single time. But if your true value is only 0.29%, this would be an effect size of just 1%. As you can see, the power of your test is very small. And that should kind of make sense. If the null value is p equals 0.301, and the true value that you're sampling from is 0.29, because these are so, now you should reject because they're different. But when you get a sample, you're going to get a sample that's probably like 0.28 or 0.29 or 0.30, and there's a good chance that you will not reject because it's close. But if this value is like 15%, now you're probably going to get sample proportions of like 14 or 15 or 16, and you have a really good chance of rejecting because the true value is so small. So effect size is the most influential factor for changing the power of your test. The second major factor that influences a test is the sample size. And I guess I could illustrate that on this applet also, even though it's not really the right applet, but please bear with me. Sorry. So right now, let's keep the effect size the same. 30% null, 25% true value, power is about 0.558. Now, if you increase your sample size, I'm going to kick this up to 20. Watch what happens to those curves. Now, it looked like they moved a little bit, but what's really happening is the standard deviations of those sampling distributions are tightening up. So it becomes like a bigger, it's like there's more of a difference between the two curves. And as you can see, the power goes up quite a bit. So increasing your sample size increases your power, of course. That should kind of make sense. The third major factor that influences the power test is your significance level. What's going to happen with the significance level is, let's put this back down to like 20 here. What happens with the significance level is, your cutoff is going to be at 5%. Well, if I make my cutoff 10%, then my rejection region, I guess I just changed the slider, 10%, then my rejection region is twice as big. And because I moved the critical value over, I also get more power. So increasing your alpha level also increases your power. But you don't want to increase your alpha value. In fact, you should run it at 0.5, so you don't really have a whole lot of control over that. But if you increase it, it does increase your power. So, and you can read through this if you want. So bottom line, this is what you need to know for the test. If you increase your effect size, it increases your power and therefore decreases the probability of a type 2 error. If you increase your sample size, that increases your power and it decreases your probability of a type 2 error. And if you increase your alpha, it increases your power and it decreases the probability of a type 2 error. All right. Now, you don't really have a control over these. You don't really have control over the effect size. You don't really have control over the alpha value because you're not supposed to change that, or usually the alpha is the probability you commit a type 1 error, right? So if you increase that, then you increase your chances of making a type 1 error, which is usually the more serious serious mistake. So really, the only thing you can do in practice, in the real world, is increase your sample size, which costs money and time and resources. Okay, this page really is kind of a little extra thing, just kind of to show you there's more powerful software programs that can analyze power. I think this is kind of interesting. So our null hypothesis is that p is equal to 0.4. And what this does is this will find different comparison. It'll give you the power for alternative comparison proportions. So this is power on the y-axis, and this is your comparison proportion. So if your null is 40%, if your true value is 40%, then you got very small power. Actually, if the true value is 40%, the probability you reject the null is actually going to be 5%. It's going to be your alpha value. But if your true value is 39%, so you got a very small effect size, you can see our power is going to be right around 10 to 20%, depending on the sample size. Now in this one here, we plot it for 3 different sample sizes, so you can get power for 3 different sample sizes. Now, if the true value is 35%, then you can kind of project up here and say, well, if I have a sample size of 500, I got about 75% power. But if I have a sample size of 1,000, now I'm going to have about 92% power. And you can kind of see how the power changes for different alternate values and for different sample sizes. And you can actually put in more sample size curves into this program if you wanted to. Anyway, there was some software that does some pretty amazing things, but we don't really have access to it in this class. So, all right, one last example, and then we'll be done with section 9.2, but let me finish this in the next video.